Good day, everyone. This is Moe Shahram, and this is Physical Science Survey course, PSCI 10 at West Valley College. And today we are going to cover Chapter 4 about heat and temperature. So we are going to talk about phases of matter and then move on to talk about the kinetic molecular theory that lead us to define the concept of temperature and heat. And then we distinguish between the temperature and heat, which is very important. And then move on to talk about how do we measure temperature, and we will discuss what happens if you heat an element or substance, how fast is going to heat up or lose its temperature, and the concept of a specific heat. And then we will talk about how the heat gets transferred from one object to another, and what are the mechanisms. We conclude with very briefly talk about the laws of thermodynamics. Looking at different matters and substances around us, we know that they are in the form of solid. We are very familiar with that. Many things are in the form of solid, and a lot of things in the form of liquid, water, milk, oil. And then some that are in the form of a gas, which we notice, or some we don't notice it, steam, vapor, and so on. And then we also have things that we probably don't notice as much. It's in the form of a plasma. Examples, when we look at the room temperature, your desk, your pencil, your computer are in solid form. And you have things in liquid state. And obviously the atmosphere is in a gas state, and things like neon sign or auroras that you see in the northern hemisphere are in the plasma state. So let's look at each one in more detail. When you look at the solid, it basically it has a definite volume and shape, a three-dimensional volume and shape, and the atoms and molecules in the solid are fixed in place. However, they constantly vibrate with respect to each other because there are forces involved there, and the temperature of that solid provides energy for them to vibrate and move in place. And that is very important because as we reduce the temperature of that solid, those vibrations become slower and slower until we get to what we call it the absolute zero, when all those vibrations cease to exist. We cannot get to that point, however, but theoretically, that's what happens. So at any given temperature, even the ice, the molecules that are there, the atoms that are bounded in the form of a crystal, they're all actually vibrating in place. So there is a motion there. If you look at the solid, there come in different form of shapes. The one shape is the what we call it a crystalline or crystal solids. For example, silicon is in the form of a crystal, and if you only have pure silicon, atom molecule can kind of bound next to each other in a very repetitive and orderly manner, and that's called a crystal. Diamond, for example, is another example. Quartz. These are one form of the solid. Now you may have different lattices exist in one element, which could be silicon, but they have different sections that have different orderly crystal, and those are called polycrystalline. And a good example is when you look at these solar cell panels. Some of them are monosilicon, which they have a little bit more efficiency than polysilicon. The monosilicon you can tell by the shape and the color of it, because they're all, uniform color, usually black. And polysilicon are kind of mixed color there. They're usually less efficient anyways. State, and then you move on to amorphous solids. Amorphous solids are the molecules and bonds in a random way together, and they're easier to kind of move them around or bend them. So when you have a piece of rubber, you know that rubber, you can bend it, and that's in the form of a amorphous solid, but it still is a solid. Butter or cotton candy are another examples. But you can move them around, you can reshape them. Then we move on to liquid, which molecules and atoms now, they're not really bound together. They slide against each other, they move around against each other, but they can take the form of the container. They can, as I said, slide, rotate, or vibrate. And if you increase the heat, what happens, they can actually escape from the surface of the liquid and into the space in the form of a gas. Then we have a gas, which atoms and molecules are usually not in contact, so they're, close proximity, and they can collide with each other, and obviously they can move around, they rotate, they can vibrate, and everything is randomly moving around. The gas, basically, if it is contained in a container, it can take the shape of the container. But if it's not, then they can scatter in the space. Then if you heat up the gas enough, what you will do, actually, you take these molecules and atoms and you strip off the electrons from them, because now the outermost electrons are experiencing energy from the heat, and they can disconnect themselves from the atoms or molecules, and by doing so, then you turn the atom and molecule into an ion. So now you have a region that has a positive ion and a negative electrons, and that is a state of plasma. Some examples of a plasma is when you look at the lightning, for example. When the lightning happens, and we'll talk about why the lightning happens later on, the amount of energy that's released, it ionizes atmosphere near those lightnings, generates plasma in those regions. Plasma happens in all the stars because the temperature is so high that atoms cannot held together their electrons, so they are in form of a plasma. Other examples in auroras, as I mentioned, in northern or southern hemisphere, when the high energy particles are hitting the molecules of the atmosphere, they ionize them and energize them. They move around, and once these ionized or charged particles are moving or oscillating, they emit light. And we will talk about how that happens again later on. And of course, neon lights are inside those tubes. You generate plasma, and those plasma, because particles are oscillating, they generate light. So in a nutshell, phases of matter happens as a result of temperature change. Of course, pressure is also factor, but right now we say at the given pressure, if you increase the temperature, you gradually make the molecules and atoms to vibrate more and more, and they need more room because they start moving faster and they elbow each other away from each other, so they actually expand and they form in a form of a gas or a plasma from a liquid. Or if you reduce the temperature or take away the heat from them, what happens, they kind of get closer and closer together and bond together, but still they do those vibration in the form of a solid. So let's now try to define temperature. Go ahead and rub your hand and you feel the warmth, right? What's happening there? Well, there are molecules, atoms on the surface of your hand, and by rubbing, you're kind of moving them around a little bit, and friction between them causes a heat. So you increase the heat because of their motion. Now, important thing is this motion and the friction between them, it's what is you feeling as a hotter temperature. So when you're looking at temperature, you're basically talking about the average kinetic energy of atoms and molecules in a given substance. How fast they move or how slowly they move, that is what the temperature actually indicates of that substance. So average kinetic energy of atom molecule in a substance is a measure of a temperature. Now, if they move faster and faster as you increase the speed of them, their temperature goes higher and higher. And if they're moving slower, the temperature reduces. So this relationship is called Boltzmann speed distribution. It tells you what happens to the temperature of a substance as the speed of those atoms and molecules increase or decrease. The formal definition of temperature. Temperature is the measure of average kinetic energy of atom molecules making up a substance. Before you had some notion of temperature, so this is too hot, this is too cold, or the weather is hot, the weather is cold. Now, think about it as what's happening in the atom and molecule scale of that substance. If the weather is hot, the molecules and atoms of the weather, the atmosphere are really moving around a lot more energetically, so the kinetic energies is higher. When you boil the water and the steam comes out, the molecules and atoms are now moving very, very fast and randomly. Or in a solid, the vibration of those molecules and things in place, they're faster and faster. It becomes hotter and hotter, and then the temperature goes up. So as one thing that we learned is that when the temperature goes up, normally most of the substances, they kind of need more room for their atoms and molecules, and therefore they expand. There is an exception, water. And we're going to talk about water when we talk about chemical solution. So that's the one exception that actually it's very, very important exception, because when you reduce the temperature of the water, it turns into ice, it actually expands as opposed to what we said. And that's a very, very important property of the water that actually is responsible for the living species on the earth. And we'll talk about that later. But for now, let's concentrate on how we can take advantage of this expansion and contraction, heating some elements, and make ourselves a thermostat. Now we make a thermostat, we have a tube, we put some alcohol in there, and make it color so we can see it. This indicates what the temperature we are at. Or if you have two different solids, for example, brass and iron, they expand at different rate. So if you join them together and expand them. One expand more than the other one, so it bends the other one. You can use that to use a switch for thermostat. If the weather is cold and you want to heat the room, you use this thermostat and you heat the room. One of the metals, which we call it the bimetallic strip, pushes the other one off, and then the circuit disconnects. When the circuit disconnects, the heater stops. And then when it gets colder, then when it connects back, then the heater comes on again. So those are the means we use to take advantage of this expansion and contraction. Of course, there are different types of thermometer. You have alcohol thermometer, mercury, thermometer that you use to measure temperature of your body. And how do we use this? Well, we use two reference points. One is the freezing point of water, and the other one is the boiling point of water when it starts steaming. We call those 2 points as a reference point, and we make ourselves a thermostat. We call it a Celsius, and 0 would be the ice point when the water freezes, and 100 we assign to as when the water starts steaming while it's boiling and you see the steam coming out. That's 100. So then we divide between 0 and 100, 100 scales, and we got ourselves. And you can go below the 0 to measure the cold temperature of the ice or things that are colder, and you have made a thermostat. There are other types. One is called Kelvin, that is used in scientific community. This one basically assigns 273 degree when the ice is formed, so it corresponds to 0 point of Celsius, and then divide 100 scales all the way to 373 Kelvin. It's same scale divisions between these two. So there are 100 between 273 and 370, and 100 between 0 and 100. And then also extrapolate downward you go all the way down to 0 degree, 0 Kelvin. We don't say degree, we say 0 Kelvin. And that is the absolute zero, okay? That's where, as I said, all the motion of atoms and molecules in a substance cease to exist. So no more motion, no more kinetic energy, no more temperature. Then we use Fahrenheit, which we all familiar with and use all the time. We assign 32 as the ice point, and 212, okay, as the steam point. So the scale here now is a little bit different than these two. Therefore, we have to find the relationship between these so that we can convert one to the other one. If you're giving me a temperature in Fahrenheit, what would that be in Celsius? But notice that Celsius and Kelvin, between ice point and steam point, is 100 degree, and that's how it extrapolates and throughout the whole range of this thermometer. And for Fahrenheit 3222, it's 180 degree. Okay, so the scale divisions are different. Now, how do we convert? Easy. If you are giving me a Celsius temperature, all I have to do add 273 and I get Kelvin. If you give me a Kelvin temperature, I subtract 273 and I get Celsius. Now, if you give me a Celsius, then I have to multiply that with 1.8 and add 32, and that gives me Fahrenheit. If you give me a Fahrenheit and want to find out what the Celsius is, you just subtract 32 and divide the whole thing by 1.8, and that's what you get. Keep these formula handy. If there is an example, you can use that, give the answer. So let's do an example. So we have a temperature of the human body is T Fahrenheit is 98 degree Fahrenheit. What is in Celsius? So we use this equation here that we just introduced. So T Celsius is equal to, so would be 98 degree minus 32 degree divided by 1.8. And when you do that, you get 36.7 degree Celsius. Now, what temperature reading is the same on the Fahrenheit and Celsius scale? So look at these. There's bound to be one number that is same level. What's that? We can still use the equation that we have that connects or relates the T Fahrenheit to Celsius. This is the one we just introduced. You want to find out which they both show the same number. So rather than this, I just say T would be 1.8 T plus 32. So if I take this T at the other side, so I have T minus 1.8 T is equal to 32. Factor the T, so you have T would be 1 minus 1.8 is equal to 32, and then T is equal to 32 divided by 1 minus is 0.8, so that's minus, so that would be actually minus 40 degree. Now let's talk about the concept of heat. Now you understand what temperature is. Okay, temperature is the kinetic energy of the molecules inside that element. What is heat? Well, heat is an internal energy that is transfers from one object to another. So one object has a certain internal energy. The other object has less internal energy. Now, bear in mind, kinetic energy has to do with just motion, okay? There is also potential energy between these molecules. Total energy would be E total would be the E kinetic energy plus E potential energy. Okay, so that whole thing is called internal energy. So when we talk about internal energy, energy that one object has compared to another object. Now you bring these two objects next to each other, what happens? The one with the higher internal energy, the energy transfers to the cold side. So the concept of heat is actually transfer of energy from one object to another. So when you turn your oven burner, the flame, it's a lot higher internal energy of the gas that is burning. That heat transfers to the pot. That is the transfer of energy from higher temperature to a lower temperature. And it always goes from higher to lower. There's not a case that the temperature goes from cold to hot naturally. No, I said naturally. There are ways we can make temperature go from a cold to the hotter, but we have to do something about it. So naturally, when you leave those two objects, one hot, one cold, always there is flow of energy, heat energy from high. Now, when we say heat energy, what is a heat? It's energy. So it has the same unit as energy. Now you can distinguish between temperature and heat. Temperature is just average kinetic energy motion of the particles inside a given object, whereas heat is internal energy of that object being transferred to another object which is at a colder temperature. Again, as I said, the internal energy consists of kinetic energy and potential energy of substance. When you look at a gas, just to say hydrogen gas, one atom in a region. So that has a translational kinetic energy. It moves around the kinetic. When you look at a molecular gas, like region of atmosphere, which has molecules, okay? So you have vibration, you have rotation, and the kinetic energy. And then when you look at a liquid and a solid, in the liquid you have the molecules rubbing against each other, sliding against each other, or moving in place as well. In a solid, obviously, remember, the electrons can move around in solid. Although the atomic sides can vibrate in place, but the electrons can also move around. So that also contributes the total internal energy of the substance. Heat is a form of energy. Suppose you're pushing this car. Obviously, you're exerting force, and then against the friction force. And as a result of this friction, you're generating heat energy. So some of that work that you do, work is energy, remember? When you push that work is actually heats up, and that interface and goes into this object and to the floor and to the space. So that heat is transferred. Now, what is the unit of the heat? Well, we said it's same nature as energy, so must be same as energy. We remember the energy and work had the same unit, and they were joules. Now heat has also the same unit, which is joule. We also use different unit for heat when we deal with things that we eat or consume, and that's called calorie. The relationship between them is the conversion factor is 1 calorie is 4.186 joules. So you want to keep that in mind and use it whenever is appropriate. Sometimes calorie is kind of not much of an energy, so then we have to multiply that by 1,000. So when you do that 1,000, we call it kilocalorie. And then we show it with the CAL, but with the capital C. Whereas the calorie, we show it with small c, CAL. Okay, so what is that? Well, it must represent something, right? 1 calorie is how much heat energy you need to get 1 gram of, a tiny little gram of the water, pure water, to raise its temperature 1 degree Celsius. So that's the definition of 1 calorie. The heat energy that you need to raise 1 gram of pure water in 1 degree Celsius. Now, that you have to do it at atmospheric pressure. But what is atmospheric pressure? When you apply a force on a surface, that's you're applying a pressure, because now you have a defined surface. And if you apply 1 Newton in 1 meter square, that is definition of Pascal, 1 Pascal. So atmospheric pressure, standard atmospheric pressure is 1 Pascal here. But we'll get back to this later on when we talk about the concept of pressure. There are other units of heat when you deal with air conditioning and things like that. And that's called BTU. That's a British thermal unit. And definition of that is that amount of heat energy required to raise 1 pound of water now by 1 degree Fahrenheit, again at the standard atmospheric pressure. If you want a conversion between BTU and joules, this is the conversion. So 1 BTU is almost 1,000 joules. All right. So if you look at your air conditioning or your heater, there is a plug in there. It tells how many BTU you can put up. That's what it means, the amount of energy that it's capable of producing. Now, the question is, suppose you have a wood stick and an iron stick in your other hand. So you go to your fireplace and put tip of those on the fire. You're holding the other end. What happens? Soon, the one that has iron is going to get hot and you have to let go because it's going to burn your hand. But the other one that has a wood, you can hold it for a long time. It catches fire at the tip, but you can hold it a long time still. Nothing happens to your hand. So different material have different characteristics against the heat. Some material heats up very quickly, some don't. For example, if you have a kind of copper pot, it can heat up quicker than if you have an aluminum pot. So if you try to boil the water, you see that some pots heat up the water quicker than the other one. That has to do with the property of atomic structures in those pots. And that's called a specific heat capacity. In other words, how fast or how slowly that material heats up. Here, if you apply the same amount of heat to a 1 kilogram gold and 1 kilogram aluminum, the gold quickly heats up to 90 degrees C, whereas aluminum stays around 30 or 25. So that has to do with the nature and structure of the gold versus aluminum. Suppose you have 10 grams of aluminum. You have a thermometer, it's sitting at 20 degrees C. If you want to heat that up to 100 degrees C, it turns out that you have to put 176 calorie heat to get it up to 100 degrees C. Now, if you want to go the other way around, if you have aluminum that is at 100 degrees C and you want to come down to 20 degrees C, Celsius, then you have to take away 176 calorie from it to get to 20 degrees C. Now let's try that for copper. We have again 10 grams of copper here. In order to do the same thing, in other words, go from 20 degrees C to 100 degrees C, you need only 74.4 calorie heat, and vice versa. And you try gold now. 10 grams of gold going from 20 to 100, you only need 24 calories. So you see, some substance, some elements require more heat to change their temperature. We show the heat with Q, and we show the mass of this with M, and the temperature we show that with delta T. So delta T here is 20 to 100. There must be something else here that we can relate all these together, and that is what is called the specific heat, that little c here. The specific heat of aluminum is 0.22 calorie per gram per degree C. For the copper is less, 0.093. For gold is even less than that, 0.03. In order to relate these things, so you must add that specific heat there. So then you have a relationship here. Now you know, if you know the mass of the object, if you know the specific heat of that object, and you know you want to go from 20 to 100, I can tell you how much heat you have to put in by using this relationship. So let's look at that more closely. Q is the applied heat. C is specific heat of that particular element. The mass is obviously M. We know what that is. The amount of temperature change is delta T. Then we have this relationship, which you can write it this way or you can write it that way, depending on what you're looking for. If you're looking for finding the specific heat, you write it this way and give me the heat, give me the mass, give me the change of temperature, I'll give you the specific heat. All right? So what is the unit of this? C. So look at this. C in this case is Q over M delta T. Okay? The unit for heat is joules divided by. The unit of mass is kilogram, right? And the unit for temperature or change temperature is degree C. We show that with a little. It could be with Kelvin, or you can write it in Fahrenheit. You can write it in terms of gram, you can write it in kilogram. If you write it in terms of joules, you use kilogram, okay? If you write it in terms of calorie, you use gram. These are the units that we use for a specific heat. Okay, what can we conclude from here? If the specific heat is high, as you saw in the case of aluminum, it's harder to heat up that element or take heat away from it. So the greater the specific heat, the greater its capacity to keep the heat or not lose it. So that's why we call it a specific heat capacity. It turns out that different substances have different specific heat, and water has the highest heat capacity. Let's look at some examples here. Aluminum specific heat is in terms of joules per kilogram Kelvin is 897. Compared to water, 4,181, and there are others in between. Here's another example here. There's a lot more. Notice that ice has lower specific heat, 2100, as compared to water, 4186. And the seawater is less because it has impurity. This is for pure water. Some of the smaller specific heats are like lead, platinum, tungsten, easy to heat. Let's do an example. So we want to find out how much heat energy in kilocalorie does it take to heat 100 grams of bathtub from 12 degrees C to 42 degrees. So we just use the equation that we have here. Q is equal to mc delta T. All right. So M is 100, delta T, so that's 30 degree change of temperature, degree C. And the specific heat of water, you look it up in the table, is 1 kilocalorie per kilogram degree C. So you multiply these together and you get. So now let's say you want to heat this with the electricity. Utility company is charging us 0.45 or 45 cents per kilowatt hour energy. So we want to find out how much it costs to heat that bathtub. We know Q is that much. We just find that out, okay? This should be to the power of 3. It's a typo here. Now you need a conversion because these are all energy, right? So you can convert energies. So kilocalorie, 1 kilocalorie, you look it up again, is 0.00116 kilowatt hour. So all you have to do, you multiply that by the amount of heat energy. So this is what we had up here, times this amount of kilowatt hour energy, times the amount they charge us, which is 45 cents. So you get $1.6 to heat that bathtub. All right, now we look at how the heat transfers from one object to another. What are the mechanisms? All right. Well, we have to consider heat transfer from solid, heat transfer from gas, heat transfer from fluid, and all that. So let's look at it. When you're near a fireplace, if you have an iron stick, hold it on the fire, soon you feel the heat on your hand. That heat is transferred by the mechanism of conduction, because all the molecules and atoms here, they heat up and they send that energy to the next atom and the next atom and the next molecule and so on until it gets to your hand very quickly. So that's a conduction mechanism. On top of the fire, because the air is heat up, when you hold your hand, you feel the warmth. So that's convection. Now on the side, you still feel the heat because of the glow of that fire, and that is radiation. So these are the mechanisms that the heat can transfer. All right, let's look at each one. And always the heat transfers from hot region to the cold region. Conduction. We have a piece of metal, for example, and we heat one side. We know that these atoms and molecules, they already vibrate. When we heat them, they vibrate more. And that vibration transfers the energy to the next, and to the next, and to the next, until it gets all the way to the other end. And that's how the mechanism of conduction works. You need that media, you need that metal for it to conduct the heat. How fast or how slow this is conducting depends on how these molecules are bound in iron is different, aluminum is different, gold is different. It depends on what we call it thermal conductivity. Some have a very good thermal conductivity, such as silver. Some have poor, aluminum. We have to find out how heat conductive is particular element. Some materials are very, very poor conductor, like wood. They actually don't conduct heat through them. I mean, they can burn, but you can hold wooden stick on the fire and your hand is not gonna get hot. If we look at what we call the thermal conductivity, and thermal conductivity is measured in watt per meter per degree C, for the air is very low. So air doesn't conduct well as compared to silver, for example, 429. Copper is pretty good. Aluminum is okay. That's why, the aluminum foils, you put it in the oven and you take it, still you can touch it. Gold is high. PVC is low, and wood is low, and water is low. That basically tells you how the heat is conducted. But of course, there is also electrical conductivity, which we will cover later. Now, let's ask a question here. Suppose you're coming out of the bath, you put one foot on a carpet and the other foot on the tile. Question is, which one has a higher temperature? What do you think? Which one feels colder? Your foot on the carpet or your foot on the tile? Well, the foot on the tile feels colder. But does that mean the tile is a lower temperature than the carpet? No. They both at a room temperature. If you have a thermometer, you measure the temperature of the carpet and measure the temperature of the tile, they both read the same number. But why is it that your foot on the tile feels colder and your foot on the carpet feels warmer? Because of the conductivity. Your foot is hotter than the tile and is hotter than the carpet. What happens, heat goes from hot to cold. It sucks the heat from your foot to the tile very easily. It's conductive. Thermal conductivity is good. And you feel colder because your heat is taking away from your foot. Now the other foot is on the carpet. Poor conductivity. So the heat is not being taken away from your foot. Although the temperature of both tile and the carpet is the same, and the temperature of both of your feet are the same initially. So keep that in mind. It's not that tile is colder temperature than, they're both at the room temperature. They have the same temperature. So it's how the heat is conducted, it's taken away from your foot. Question for you. If you hold the handle of a steel pot full of ice, the end in your hand will soon become cold. Does cold flow from the ice to your hand? What is the flow of heat? The answer is no, because the pot is taking away heat from your hand. And the fact that the heat is being taken away from your hand feels colder. So this may be counterintuitive, but this is what it is. The second mechanism is convection, and that applies for fluid. Now, when we talk of fluid in general covers both gas and liquid. In the case of the air, so you have a heater here. Okay, the heat basically heats up the air here, and that air rises up. The colder air is on the bottom, so it kind of pushes back down, and so it creates a convection, a movement of air. The hot air circulates, and that is the mechanism of convection. But why is it that air rises up? Well, when we have a hot air, remember, the molecules are moving around more, so they need more room. So the density of the hot air are less than cold. So now you have a volume of air with, energetic gas molecules, less dense than the cold air, so less dense rises up. You put a piece of wood in the water, push it down, it just comes back up because it's less dense than the water. Same thing happened here. The less dense hot air rises up, and as a result, that kind of creates a circulation. Now, desert community sees a huge variation in temperature. It gets very hot during the day and very cold during the night. Why is that? Well, it has to do with what we covered about specific heat of the land or earth. If you look at the table, the specific heat of water is 1 kilocalorie per kilogram per degree C. What earth is 0.19 kilocalorie kilogram per degree C. Which one gets hotter easier and loses its heat easier? The earth. The water holds onto the heat. It heats up slowly, but once it heats up, it holds on to the heat. Whereas the land heats up quickly and loses the heat quickly. Now, as a result of this phenomena, we know that everywhere near the coast, coastal properties are more expensive and desirable. Why is that? Because the weather, it's more moderate there. It doesn't fluctuate so much. Why is that? Look at it. During the day, when sun shines on the land and the sea, Earth quickly heats up, let's say, to 72 degrees Fahrenheit during the day. So once this heats up, the atmosphere, the air heats up and rises up. On the seaside, because the water doesn't heat up as quickly, so it stays around 65 Fahrenheit. This rise of hot air and the cold air over the sea, they kind of get into a convection and generate a nice breeze, cool breeze from the sea to the land during the day. So that's what you want, right? Nice breeze during the hot day. What happens at night? When the night comes, the land loses the heat quickly. It goes down below the temperature of the water, so it comes out, say, around 60 Fahrenheit. Now the air is colder near the land. But compared to the air over the sea, is hotter, warmer. So what happens then? A reverse convection happens, and the warmer air comes in and you feel not as cold. So this is what we call moderation of climate in coastal community. The third mechanism for the transfer of heat is radiation. So radiation is transferring energy by means of electromagnetic wave. You know that if you have a lamp, it glows, right? But it gets hot too. It radiates light. What is light? We will see that light is nothing but electromagnetic wave. We talk about a whole chapter about that. The light can go through the vacuum, but they need the media. In convection, in a conduction, you need the media. But in radiation, you don't need the media. That's why we get the sunlight and the heat from the sun coming to us. Millions of miles in the vacuum, in the space. Electromagnetic wave, radiation, don't need the media. Can go through the vacuum. Now, every object you can think of, it's radiating because they're at some temperature. Or could be low temperature. Even that piece of ice is radiating. But some at a higher temperature, you can notice that. The temperature of that body, of that object, it tells us the rate of emission of radiation from that body, the intensity of that radiation. And also, what's the nature of that radiation? Is it a white light, or is it an infrared radiation? Or is it a microwave radiation? Or is it radio wave radiation? One of the reasons that you go to your car in the parking lot, sitting on the sun, and you try to get in there, it's so hot there. I mean, outside maybe 70 degrees, but as soon as you open the door, you want to get in, you're maybe 100 degrees inside that. So why is that? The radiation from the sun penetrates through the windows of your car, gets in there. It gets reflected from your seat, your dashboard, and everything else in your car. When it gets reflected, the reflection would have higher wavelength than the original that came in. So the original wavelength of the light can penetrate through the window shield, but the reflected from internal gets trapped in the car. And once that happens, the temperature of the car rises up. The characteristics of the radiation is important now. We talk about the frequency of the radiation or wavelength of the radiation. We will extensively talk about that upcoming chapters. When you have a longer wavelength, it's harder for them to get out of the window shield or glass. It just reflects back inside. And that produces a huge temperature inside the car. Now, this is the same thing happen in greenhouse. A greenhouse, you put a transparent material, glass or plastic or what have you. The radiation from the sun comes in, say during the winter time, it penetrates inside. When it's inside, it gets reflected from all surfaces. But whenever that happens, its wavelength increases. So it cannot go back out. It gets trapped in there. And then you have a warmer inside the greenhouse, so the plants and vegetables can grow even during the winter. Now that same thing happens in global warming. Here's the radiation from the sun coming in through the atmosphere, hits the ground. It gets reflected. Reflection, some of it escapes. Some of it gets reflected back towards the earth. Now, if you have a layer of greenhouse gases, like carbon dioxide and other gases that we produce all the time, it gets reflected back from the greenhouse gases, and then the earth gets hotter and hotter. There's a lot of pollution that causes that greenhouse effect. And here is the pollution by different sectors. You have power station, electricity production. Waste disposal is 3.4%. Land use and biomass burning are 10%. What is the big one here? Industrial processes, 16.8. Transportation, fuel, burning fuel, 14%, agricultural byproduct, and so on. So you can see all of these would contribute. And if you want to know what are the major byproducts, greenhouse gases, carbon dioxide, methane, nitrous oxide, from where they come, for example, from agricultural byproduct, you have 62% of nitrous oxide here. And if you want more information, there's a very good article in this link, so you can go and do some more research and study if you're interested. So now let's talk about surface of Earth loses energy to the outer space mostly due to which one of these processes? It gets reflected by the process of radiation. As I said, everything is radiating. You can see that by, infrared camera. It shows you very nicely what part of your body is radiating more. Or if you look at with the satellite, you can see the auroras with the infrared camera from top on the North Pole. Okay, so the last part is a brief introduction to thermodynamics. This thermodynamics is a very detailed subject which requires a course by itself, but is beyond the scope of this course. So I'm just going to go quickly, just give you an introduction. Thermodynamics has 4 laws actually, 3, but one law is called Zero's law. This one is very obvious. So if you have 2 objects that is in thermal equilibrium with the third object, so we have B and A are in the thermal equilibrium, so they have both same temperature. And if C and A equilibrium with C and A, then the law says B and C should have also the thermal equilibrium, which is trivial, right? Then the first law, it deals with the concept of heat energy and the work and what happens to the internal energy of the system or object. So if you add heat to a system, okay, let's say it's a closed system, so there's no external stuff there. That heat increases the internal energy of the system and or does some work for you. This is a good example. Sometimes it may not do work for you, but it just increases the internal energy. But in this case, you have a cylinder, you have a cap here, so you heat up the air inside. It does work. It pushes this cylinder up because it also increases the internal energy of the air molecules inside. So that's the first law of thermodynamics. Now Q is the heat, delta U is the change between the internal energy of this versus that one, okay, as you apply the heat, okay? And the work done is how much this piston is raised to a different level. So that's the essence of the first law of thermodynamics. And the equation that governs Q is equal to change of, this should be U here, guys, delta U, not E, because different notation. So Q is equal to delta U plus W, which is the work. Or you can rewrite that in terms of delta. Application of the first law is that, hey, you can actually make a heat engine, make the train to move. You heat up water, the internal energy increases, pushes some sort of a piston here. The piston can turn the wheel for you. So there you go, heat energy, first law of thermodynamics. Having that in mind, we cannot build a 100% efficient engine because some of these energies will dissipate and it's impossible to make 100% efficient engines. So because not all the thermal energy can be converted to the work. A lot of it goes in changing the internal energy of the system. The second law is also trivial. It says that the flow of heat energy is always from a hotter to the cold. We already covered that. However, there are occasions that you can do the reverse, but you have to do some additional work there. For example, your refrigerator. Your piece of grocery that you buy inside the refrigerator. So what happens, refrigerator takes that heat from that piece of grocery and funnel it out to the air environment by means of electricity. What you're doing, you're getting heat from inside the refrigerator out to the environment, but you need to have that electricity to do that job for you. Naturally, that doesn't happen. Naturally, always the heat is from hot transfers to the cold. So if you want to take additional heat from the cold to the hot, you have to do some work. And we do that by plugging in the refrigerator or turning on the air conditioner. Second law says that heat never flows spontaneously, naturally from the cold object to the hot, so we know that already. These are different statements, says the same thing. Cold objects are at the state of more orderly than hot. And the heat flow naturally flows from hot to cold. Natural processes tend towards the greater state of disorder. So cold object, it's less of a disorder, but when you bring a hot object next to it, the heat flows and makes that cold thing is more disorder. So that's the natural flow. So that disorder is called entropy, a measure of disorder. Naturally, entropy of a system increases. For example, let's look at the universe. So we have stars, we have sun, there's heat, there's a lot of heat there, They radiate heat energy into the universe. So from hot objects goes to the colder object. But eventually these stars and sun heat diminishes and burns out. The entropy or disorder of universe goes to a higher state. But if you look at the living organism, it's a different story, because now you get the energy input into our system. Our system is orderly, functional. In a living organism, the entropy basically decreases. So the third law tells us that we have an absolute zero, and at absolute zero, all the motion of the particles, atoms, molecules, everything cease to exist. So that's called 0 Kelvin. Now, if we have an isolated system like this crystal, and you decrease the temperature to 0 degree, the entropy of a perfect crystal of a pure substance approaches 0. Now, the other way, if you increase the heat, the entropy becomes larger, increases. So that's basically all we want to talk about in this chapter. And this concludes the chapter 4 about heat and temperature. So have a good day, and I will see you next time.